Welcome back to Chem Talks once again. Today, guys, we are going to continue talking about energy. And today we're going to relate energy to the state that we find matter in. Is it a solid? Is it a liquid? Is it a gas? And also we're going to look at the intermolecular attractions that hold those particles together when they're in their various stages. So let's first start off by talking about some of the background in this, what we call the kinetic theory. Kinetic theory describes the state of matter, solid, liquid, and gas, in terms of the energy of its particles. Okay? It states that all particles in all form of matter are in constant motion, and this motion is what determines what state is in. Is it solid? Is it liquid or gas? Okay, and this energy that we're talking about is kinetic energy, as we talked about earlier in one of these podcasts. We said kinetic energy is the energy an object has due to its motion, as opposed to potential energy, which is due to its position. So energy is related to an object's temperature. The higher the temperature, the more energy it's going to have. So the more temperature, the greater the temperature, the greater the motion. So as particles begin to slow down, they are cooled. Okay, so as they get cooler, they have less energy, they begin to slow down, they don't move quite as far. And they have a tendency to lose or give off energy as they are cooling. On the other hand, as particles are heated up, they speed up. There's more energy to make the particles go faster and faster, and the matter gains energy. Okay, what we see then is, as we said, all substances have energy due to the motion of the particles within them, except for a special case. And that's when we get really, really low temperatures, which we already talked about at absolute zero. If you remember, absolute zero is the coldest theoretical temperature that can exist. It's minus 273 degrees Celsius or 0 degrees Kelvin. Now, at this point, all molecular motion is stopped. Okay, but above that, above 0 Kelvin, all particles have motion. Even if it's just a little bit, they still have motion going on. So let's talk about, or just review the three states of matter. The first one is solid. In solids, the particles are closest together and they're at the lowest energy. The particles aren't moving very fast. Because they're not moving very fast, they have a fixed volume and a fixed shape. Think about a piece of wood, right? Its volume is not going to change and its shape is not going to change as well. Okay, and that's due to the fact that the particles have very low energy. Now, if we add more energy, we can get a solid generally to go to a liquid. The particles start moving farther apart because they have more energy. Now, even though they're moving farther apart, there's still not enough energy for them to break free. So the volume is going to be held constant, but the changing shape. Imagine you have a water bottle, an Nalgene bottle, filled halfway full with water. No matter how you turn that water bottle, the volume is not going to change, but the shape will change. Now, one more. We can add even more energy and get to our gas state. In this, we are getting so much energy that our particles are starting to pull apart, and their gas occupies its entire volume that is contained in. So it has a changing shape and changing volume because it has so much energy. Think about an ice cube or water, right? In the solid, it's going to stay the same. We add some heat, it goes to a liquid. The volume pretty much stays the same, but the shape changes as it melts. But then more heat, we come to gas. We make it steam, and that's going to fill to expand the room. So its volume changes, and so does its shape. And so phase change occur when the molecules either begin to move farther apart or closer to each other. When this happens, we're either increasing or decreasing the kinetic energy. Generally, we think of this as increasing the temperature or decreasing, because when we increase the temperature, we're getting more energy. When we're decreasing it, we're getting less energy. So when this happens, it causes the bonds between the molecules to be broken or reformed. And this forming or breaking of bonds results in a phase change. This bonds we're talking about are what we call intermolecular attractions or intermolecular bonds. Okay, these are bonds that are between different molecules. Okay, it's due to electrostatic attraction. Remember, electrostatic attraction is a positive plus a negative. Opposites attract. Now, we talked about this type of attraction earlier when we talked about intramolecular bonds. Okay, intramolecular bonds are the bonds that hold a single molecule together, either ionic or covalent. Okay, they're ionic or covalent bonds. But they're relatively strong compared to these intermolecular bonds, which holds one molecule to another. It's these intermolecular bonds that determine the phase. And now they're relatively weak, so we can break these bonds, which results in a phase change. Okay, so it's these intermolecular bonds that are responsible for whether a substance is a solid, liquid, or a gas. Let's look at an example. We have hydrogen chloride here, and then we have carbon dioxide here. Holding these individual molecules together here in the pink are intramolecular bonds. The covalent here, or the ionic here, or covalent here. Now, between the different molecules, between here and here in the orange, we have these what we call intermolecular attractions, are relatively weak. Okay, but they're strong enough to keep these molecules together and create the different states of matter that we've talked about. So let's talk about these types of intermolecular attractions. There are actually three major types that I want to discuss. The first one is called dispersion forces, also known as London forces. We have dipole-dipole interactions. And then finally, hydrogen bonds, which are actually just a type of dipole-dipole interactions. Let's start by talking about the dispersion forces. Dispersion forces, also known as London forces, are named after Fritz London, who first described these forces during the 1930s, just to give you an idea where the name came from. What it is, it's an intermolecular force attraction between what we call induced or temporary dipoles. If you induce something, you kind of force it to become a dipole. Now, if you remember back from when we talked about covalent bonding, we talked a little bit about dipoles. All dipoles are polar molecules. Molecules that have one end slightly positive, the other end slightly negative, but overall they have a neutral charge. Okay, so these London forces, dispersion forces, are going to form between nonpolar molecules. That is, molecules that generally don't have this positive and negative side, generally where they're sharing them equally, but we can induce these temporary dipoles. Okay, these dispersion forces, like we said, are formed by these temporary or induced dipoles. Okay, they're formed by the shifting of the electron clouds within the molecules. Remember, molecules are in constant motion. Okay, and as they're in motion, they have a tendency to collide with one another. And when they collide, this causes the electrons to shift. Okay, so when they shift, you get a slightly positive side on one part of the molecule, slightly negative on the other, and they form these temporary dipoles. Well, if you have positive and negative, they become attracted to each other in opposite molecules. But it's just a quick one because it shifts, the electrons shift, and then they shift back. Okay, so it's, like we said, it's only temporary because they're always constantly moving. So because of the constant motion of electrons, an atom that normally is nonpolar can be turned into a temporary polar molecule. So for example, here's a molecule. Just look at the electron clouds. Generally the electrons are going to be scattered all around. Let's say they kind of run into each other. And all of a sudden we get a shift of the electrons to one side. Well, this causes a slight negative side on one, slight positive on the other side. And then same with this other one. Here's more electrons over here, so we have negative. Less over here, that should be positive, not negative. So we see this positive here becomes attracted to that negative. And that's where we get these temporary dipoles and we form these dispersion forces. So dispersion forces are temporary dipoles. The second type is what we call dipole-dipole. And these are formed when the positive and negative ends of different polar molecules align with each other. The important thing to remember that the force between neighboring permanent dipoles. So these aren't caused by the shifting of electrons like the dispersion forces. These are permanently polar. So they're a little bit stronger. They're going to hold together a little bit longer. Okay, let's look at carbon monoxide. Carbon monoxide is formed by carbon and oxygen sharing electrons, but they don't share them equally. Okay, what we see is that it forms a polar molecule because one of the molecules is going to hog the electrons more than the other. So, for example, oxygen is going to hog more of the electrons, making it slightly negative. Carbon is going to be slightly positive because most of those electrons are over here. Well, what happens then is that we get a bunch of these lined up. And we line up by opposites attract, electrostatic reaction. Okay, so the negative end of one lines up with the permanent end of another here, and then here's another example. And we get these electrostatic attraction going on, which forms this dipole-dipole bond, okay, or another type of these intermolecular forces. Third type is what we call hydrogen bonding. And hydrogen bonding is a special type of dipole-dipole interaction, still between permanent dipoles or permanent polar molecules. But what we see, it's rather than being any polar molecule, it has to contain a hydrogen atom. So it's attractive force between a hydrogen atom and one polar molecule and a negative atom and a second polar molecule. Okay, it's the strongest of the three intermolecular forces. But we got to remember, these, even though it's the strongest of three, it's still weaker than the intramolecular forces that create ionic and covalent bondings. So it generally will form when hydrogen is bonded to elements such as fluorine, oxygen, nitrogen, and chlorine. Okay, I probably won't ask you on a test, but understand that it's just a special type of dipole-dipole that involves a hydrogen ion, or excuse me, a hydrogen atom. Best example of this is water, H2O, right? Water hogs the electron, so we get it over here, and here's the hydrogen, its electrons over here, so we get this hydrogen bond going between them. Okay, and this hydrogen bond, which is really responsible for many of water's unique properties and characteristics that we've talked about early in the year. Okay, so how does this kind of all relate together? Kinetic energy, intermolecular forces, and phase change. Well, the point of the temperature at which these molecules overcome or break the intermolecular forces depends on the type of intermolecular force between the particles. So as we break these forces, we change phase. So the weakest of the three bonds, or three types, is going to be the dispersion forces, also known as London. Then we have the dipole-dipole interactions, and then the hydrogen bonds. So what this would mean is it requires more energy to change the phase of something that's held together by a hydrogen bond than held together by a dispersion bond. Alright guys, so in this episode we looked at intermolecular forces and how the energy that these molecules have relates to what phase it's in. Is it a liquid, solid, or gas? And as we add energy, we are breaking the bonds that hold these different molecules together. Now, we're not breaking the bonds that make up an individual molecule, but we're breaking the bonds that hold one water molecule to another. Remember, there's three types of what we call intermolecular forces. That's dispersion, which are caused by this temporary or induced dipoles. We have dipole-dipoles, which is all of permanent polar molecules. Or we have hydrogen, which is simply a specialized type of dipole-dipole interaction. Okay guys, if you don't understand any of this, please come and see me. We will probably do a lab on this coming up to make this a little clearer. Until then guys, take care and I'll see you in class.